All right, so good afternoon to all of you. We'll resume our discussion on chemical admixtures. So far we have looked at water reducing agents, then we talked about set controllers, air entrainers, right? And we also then talked about viscosity modifiers, which required some additional understanding of rheological approaches to understanding concrete fresh characteristics, okay? We'll today move on to corrosion inhibiting admixtures and other specialty admixtures that are typically used for concrete applications. So, yeah, just a repeat of what I just said. So, before we look at corrosion inhibiting admixtures, it is important for us to understand the mechanisms that lead to corrosion, okay? So, idea is to see what conditions in reinforced concrete can promote corrosion and how do we lead to a protection against corrosion. Yeah, that's the kind of strategy we'll adopt for this chapter. Now, as you know very well that steel and concrete make a very good combination. Steel is a perfectly good reinforcement for concrete. For what reasons? What are the primary reasons? There's a strain compatibility because the coefficient of thermal expansion of steel is similar to that of concrete, and in general, the bond between steel and concrete is also good. It's further enhanced obviously by the presence of the ribs that are there in reinforcing bars, right? Over the years, we have moved on from mild steel to cold rolled steel, and then finally today we are using what type of steel? TMT, but the actual correct name for that is quenched self-tempered QST steel, right? The common name is TMT, thermomechanically treated, but that's not really a correct name because most steels are thermomechanically treated, right? Every steel has some thermal treatment, some mechanical treatment. Now, steel has an inherent tendency to corrode. Why? Why does steel want to corrode? Yeah, so the stable form of any metal is its oxide. So, iron is no different, it has to stabilize by transforming to an oxide. So, there is a natural tendency for steel to corrode with time. Now, this corrosion happens in different rates in different types of environments. If you have an acidic environment, it is a much faster corrosion. If you have a neutral or an alkaline environment, the corrosion rate is controlled by several factors, okay, which we will talk about in just a brief while. But in concrete, we all know very well that the environment is highly alkaline. The pH of concrete is of the range of 12.5, 13, sometimes even more, okay, mostly more than 13. In such instances, steel in reality corrodes almost immediately. But this corrosion layer that forms on the steel as soon as you put that in concrete is actually a passive layer which prevents further corrosion. So, this thin, invisible and stable layer of initial corrosion products forms on the steel surface as soon as you embed that in an alkaline medium such as concrete. Of course, this layer may take some time to develop, but that is what happens initially to the steel as it comes into contact with the highly alkaline environment of the concrete. So, high pH of the concrete pore solution leads to the formation of the stable passive layer. Now, as you move from reinforcing steel, regular reinforcing steel to corrosion resistant steel or to stainless steel, what are you doing essentially there? What changes are you making to steel as it goes from reinforcing steel to corrosion resistant steel to stainless steel? We are adding some alloying elements, typically chromium or nickel, and these are enhancing the corrosion resistance capabilities of the steel. And this corrosion resistance enhancement is primarily because the passive layer that forms on the steel surface in the alkaline environment is much more stable in the case of the corrosion resistant steels, especially in the case of stainless steel. Okay. Stainless steel is expected to not corrode for a long time. It does not mean it will never corrode, but for a long time, if the conditions are ideal, steel will not corrode, stainless steel will not corrode. But reinforcing steel typically has a tendency to start corroding because of change in this environment in its vicinity, okay. So, let us see what happens which leads to that change. Now, before that, some basic definition of your electrochemical cell that occurs during corrosion. We know that on the same site of steel, you have an anode and a cathode. The anode is where the ion is getting converted to ferrous ion plus 2 electrons. These 2 electrons are then combining with oxygen and moisture at the cathode to produce your OH minus, right. So, that is your anode and that is your cathode. So, there is a flow of electrons that happens, which indicates the conduction offered by the electrons. Typically, the current flow with respect to conduction is in the direction opposite to the flow of the electrons, and then there is an ionic conduction that happens, right. And this conduction of the ions has to happen in the electrolyte. For steel embedded in embedded in concrete, what is the electrolyte? Concrete, right. The concrete that surrounds the steel is the electrolyte. So, the obvious understanding from here is that since ionic flow has to happen through the electrolyte, if you make the electrolyte less permeable, what is going to happen? You will reduce the flow of current. So, corrosion rate will be lowered when you have concrete of a high quality surrounding the steel, and that is the reason why we see less corrosion potential for concretes where water cement ratio is lower. So, the anodic and cathodic reactions in perfect balanced conditions are given here, okay, and the kind of deterioration that typically happens in a column that is submerged in seawater or partially submerged in seawater is given. The maximum deterioration is seen in the zone which is at the interface of the sea and the air, and also where the sea level perhaps changes because of tidal actions, and also there is mechanical abrasion because of waves, and that causes a greater level of deterioration in this kind of a zone. Okay. So, there are several mechanisms that lead to deterioration of the concrete, but primarily we are interested in what causes the corrosion of the reinforcing steel, and in seawater the agent that leads to corrosion obviously is, what is there in seawater which causes corrosion? What salt? Be more direct. Chloride. Yeah, there is chloride in seawater which causes corrosion. Now, again, just steel in water with oxygen will have corrosion happening. Obviously, you have the anodic reaction letting out your ferrous ions, you have the cathodic reaction which gives hydroxyl ions, and then the combination leads to the formation of what we call as, what do we call it? Ferrous hydroxide, yes, but what is the common name? Rust. Yeah, the corrosion product is called rust. Okay. Now, the rust can vary in its composition and therefore its color depending upon the type of compound that is forming. Early formation happens of ferrous hydroxide, then you may have ferric hydroxide, that may further change to ferrous oxide or ferric oxide, which leads to various different hues and colors of rust that you actually see. Okay. But one thing interesting to note is the anode and cathode can exist on the same piece of metal. The same steel bar can have some sides that act as cathode, some that act as anode. Now, why does this happen? I would assume that, okay, when there are two steel bars close together, one may behave as cathode, other may behave as anode. But why should the same steel bar have sides that behave as anode or cathode? Why should potential difference arise on the steel surface? Ionic concentrations may be different in different portions of your concrete. What else? What else may happen? Well, we are assuming that concrete is uniform. Yeah, actually that's an interesting case, because it may happen sometimes that the same rod may actually encounter two different concretes, but as far as possible we have to minimize that happening. The differences due to concrete have to be minimized, but steel itself inherently will have some issues. What are those issues? For instance, at this location and at this location, would there be any difference? Yes or no? Why not? No, okay. I mean, in this picture it's not described there, but what I meant to ask you is, in the ribbed sections versus the non-ribbed sections, would there be a difference? There will perhaps be some local strains in the ribbed portions which may attribute to that site being more active than the other site. Okay. What else can, your composition of the steel may not be perfectly uniform across the entire surface. Differences in composition may make one site more reactive than the other site. Okay, if you look at microstructure of steel, there are different phases present. Some are more liable to corrode as compared to the others. Now, in cold rolled steels or cold worked steels, you are doing cold working, no? You are twisting when the temperature is low. So, obviously, you are inducing some internal residual strains in the system. And those residual strains, if they are not distributed uniformly, you will definitely have some sites that act as anodic as compared to the others. Even a simple thing like a steel bar which is stored in the external atmosphere gets coated with dust at one location, and you put this without cleaning, you are then creating again differences on the same steel bar. One is covered with dust, the other is open. So, the access to moisture and oxygen is less in the zone covered with dust and more in the zone that is open. So, there are differences that you are creating on steel bar sites which are not uniform. So, that is why the same steel bar can act as both anode and cathode. And corrosion or rust formation essentially leads to cracking. And why does this cracking happen? Because your oxides and hydroxides of iron have a much greater volume than the original steel. Up to 6 to 8 times increase in volume can actually happen when steel corrodes, leading to distress or tension in the concrete outside, and tension in concrete is always accompanied by cracking. Okay. Now, as far as concrete or reinforced concrete is concerned, two major things that we need to worry about with respect to the cause of the corrosion itself. One is corrosion that is caused by chlorides, the other is corrosion that is caused by carbonation. Now, this relates to the general atmosphere in which your reinforced concrete structure is servicing. A coastal structure obviously has much greater chances for chloride related damage. And the issue with chloride is that it leads to a rapid pitting on the surface of the steel. So, the loss is more non-uniform, and that is quite dangerous, because there are some sections of the steel where the cross section becomes so small that your load carrying ability of the steel bar is not there anymore. On the other hand, in carbonation, the carbonation or the CO2 penetration into the concrete. So, let us say this is your reinforced concrete structure and that is your steel in between. So, the CO2 that comes in from the external atmosphere has to penetrate this concrete and generally moves as a front. That is the CO2 which has entered the concrete, and it more or less approaches the steel surface all at the same time. So, you get a more uniform rate of corrosion. Uniform corrosion is not as detrimental to the concrete or to the structural capacity of the concrete as the formation of a single large pit which may happen at certain locations. Okay. So, very important to understand that chloride induced corrosion can lead to much more devastating failures as opposed to carbonation induced corrosion. In what environments will carbonation happen? Generally most polluted areas, right? But more often it happens wherever the relative humidity ideally is between 40 to 80%. Maximum happens between 60 and 70. Maximum rate of carbonation, carbon dioxide induced corrosion, or rather carbon dioxide penetration is possible in the 60 to 70% relative humidity range, but it can happen all the way up to 80%. Beyond that, the concrete is almost getting saturated. So, if the pores of concrete are saturated with water, it is not easy for the gas to diffuse. There is no space for the gas to come in, and there is only so much of CO2 that can dissolve in water. But what about the other end? Very dry concrete, less than 40% RH. Why is carbonation not a problem there? Moisture is not there. You need moisture to convert CO2 into carbonic acid, and that's what leads to the corrosion of the steel. So, acidic conditions may not get generated because there is no moisture available. So, you need to have some moisture, but not a lot of moisture, right? Partially saturated systems are prone to carbonation, and then you have wetting and drying cycles that may happen because of natural exposure of the concrete, and that may also change the rate at which CO2 penetration happens. So, you have to be careful about modeling this kind of phenomenon. In the lab, we always do this with accelerated carbonation exposure. We increase the carbonation concentration and allow the carbon dioxide to move in much faster, but in reality it is much slower. What is the atmospheric composition of carbon dioxide? The concentration of carbon dioxide in the atmosphere, what you and I are breathing now, 0.04%, about 400 parts per million, right? 0.04% is the CO2 concentration. But if you look at experiments which are done in the lab, we do it at either 1%, 3%, 4%, sometimes 50% of CO2 also is used. That's very high amount, and correlating those experiments becomes quite difficult. But anyway, we need to understand the rate of CO2 penetration into concrete, and more than that, we need to understand what are the instances where corrosion will happen. For that, I will go back to this diagram here. Steel is corroding, it needs oxygen and moisture for corrosion to happen. Okay. For steel to corrode, oxygen and moisture are necessary to be present at the cathodic sites. Without that, you are not really causing or propagating corrosion, which may initiate, but propagation requires oxygen and moisture to be present. And if your concrete is impermeable, you will further restrict the possibility of corrosion because oxygen and moisture are not available. Similarly, if you are in zones where carbon dioxide penetration is high, but then there is not sufficient moisture available to cause the corrosion, you may get CO2 penetration deep into the concrete, but perhaps there may not be much chances of corrosion. And this is indeed the case wherever people see that the extent of rainfall is limited, because unless you have rain, there is no moisture that comes into the concrete. If you have prolonged periods of rain followed by periods of drying where CO2 can penetrate, again followed by rains, in such cases you need to be very careful about carbonation-induced corrosion. But if your atmosphere is mostly dry, even though the humidity may be 50-60%, you may not really get corrosion due to carbonation. But chloride, as long as it is present in the vicinity, will certainly cause corrosion. And it is not just in coastal structures that you get chloride corrosion, you may also get sometimes in inland structures where chloride concentrations are high in the groundwater. For instance, in Delhi, interestingly, the chloride concentrations in the groundwater are very high. And there is a study that was done by our environmental engineering group, which showed that the burning of microplastics also increases the chloride load of the soil, and this chloride eventually makes its way to the groundwater, and that can also lead to corrosion. Nobody would have thought this, right? Imagine, of course, most of the studies in Delhi were done with respect to understanding the issues of pollution because of crop burning, but this microplastic burning was another big problem. Like your small polythene covers and all, if they make their way into the composting yard, they get burnt, and this microplastics will release, there is chloride available in the system, and that also adds to the load of chloride in the soil. It combines with the water or dissolves in the water and is available for corrosion of the steel. So you would never imagine that chlorides would be present in a place like Delhi, but yes, groundwater there has fairly high chlorides in some regions. So this is a typical case of a carbonation-induced corrosion. You have very thin members, thin reinforced concrete members. So it is not going to take long for the CO2 to penetrate to the extent of the steel, and if there is rainfall that provides moisture, you will definitely get corrosion that leads to cracks like this. So this is a telltale sign of corrosion. Okay, all along the steel there is cracking. That is a very clear sign of corrosion happening. So to assess corrosion, what typically is done is you take a sample of the concrete and you spray phenolphthalein on the cut surface. You split it so that you expose the surface and you spray phenolphthalein. Wherever you get no coloration is the zone that is carbonated. Wherever you get pink coloration is a zone which is not carbonated, which is high pH. Right? You would have done phenolphthalein test in chemistry lab in school. So, in as alkaline environments, it turns pink, right. It is colorless when the pH reduces to around 9. So, carbonation, why does carbonation reduce pH? Because it combines with your calcium hydroxide to make calcium carbonate, and it reduces the alkaline buffer that is present in your system. Okay. So, pH reduces when CO2 enters the concrete. In chloride-induced corrosion, depending on the locations where permeability is greater, maybe because of some cracks appearing in the surface, or maybe because of some other defects that are present in the concrete. In some locations, you have chlorides entering more, and chlorides have a tendency to completely eat away the passive film. So, here the passive film is indicated by the light green layer. The chlorides will have a tendency to completely eat away the passive film, and indeed what happens is actually in the process you are actually generating more acidic environment in the system, and this acid further damages the steel. So, you get pit formation, this is called pitting corrosion. And that is really problematic because it reduces, now look at this cross section, it is now reduced by more than half. Okay. So, your load carrying capacity of the structure is getting severely limited now because of the pitting formation. Other regions may be free of corrosion, but then there are some regions where this can happen. So, your steel will just snap. You may not get a lot of corrosion products forming in this case. You are not seeing a lot of corrosion products forming. Even without that also you can cause significant damage. Okay. But of course, FeOH twice is also going to form, and that will further add to the damage by cracking the concrete. If a concrete cracks, more chlorides get in, the reaction is speeded up even more. So, if you typically look at the damage due to corrosion and you plot that with respect to time, you will see this kind of a relationship. Initially there is very little damage, then there is suddenly high damage, and finally very high damage. So, there are three essential zones. This is the zone where the steel is mostly passivated. That is because the film is intact in that zone. So, while I have put some damage here, but actually there is close to 0 damage in that zone. So, if you have to design a structure for 50 years, you have to ascertain that this passivation of the steel will not get broken for 50 years. That is a safe design. That means you do not want corrosion to start at all during the life cycle of the structure. You can also adopt a slightly more risky design approach, where you say that, okay, I will allow up to 10% damage to happen, and that will allow you to design for a greater service life, but then you need to have some detection of whether corrosion is actually happening in your system or not, and any repair is needed to further enhance the service life. Okay. So, but the problem is when it starts getting into this region beyond the passivation, the properties become unpredictable. The extent of cracking starts dictating the rate at which your chlorides come in, and because of that cracking happening, the later age damage basically increases significantly. Okay. So, again, I am not talking about modeling in this chapter, but what I will essentially talk about where we can actually start looking at solutions to increase the service life. Mostly we will want to work in this time for depassivation of the steel. That is where we want to really focus our recovery or our repair, our strategies for increasing corrosion resistance of the reinforced concrete. So, this is again an example of pitting corrosion happening in pre-stressed strands. So, you can see very clearly pit formation on the surface of pre-stressed strands. So, in pre-stressing concrete or pre-stressed concrete, corrosion of the strands is even more dangerous, because we know that we rely on that for the load carrying capacity. In reinforced concrete, there is sufficient redundancy. So, if one steel gets corroded, we have sufficient redistribution that can actually happen. A lot of cracking can happen before the failure happens, but In pre-stressed concrete, one crack can lead to complete collapse, especially when it's leading to a steel strand damage that will lead to a complete collapse.